Welcome to the fascinating world of thermodynamics. In this video, we'll explore the principles that govern energy, heat, and work in our universe. Thermodynamics is a branch of physics that helps us understand how energy moves and changes form. From boiling water to powering engines, thermodynamics is everywhere. Whether you're a student, a science enthusiast, or just curious, this journey will help you grasp the basics and see how these concepts apply to everyday life. Let's start by understanding what thermodynamics really means and why it's so important in science and technology. Thermodynamics is the study of energy, its transformations, and its relation to matter. It examines how heat and work are transferred in physical and chemical processes. The word itself comes from Greek, therm meaning heat and dynamis meaning power. This field helps us understand why ice melts, how engines run, and even how stars shine. By analyzing the flow of energy, thermodynamics provides a framework for predicting how systems behave under different conditions. This foundational knowledge is crucial for engineers, scientists, and anyone interested in how the universe operates. Roots of thermodynamics trace back to the 19th century during the Industrial Revolution. Scientists like Sadi Carnot, Rudolf Clausius, and Lord Kelvin made groundbreaking discoveries about heat engines and energy conservation. Their work laid the foundation for the laws of thermodynamics, which revolutionized technology and industry. Understanding this history helps us appreciate how thermodynamics evolved from practical problems like improving steam engines to a fundamental scientific discipline. Today, thermodynamics continues to influence innovations in energy, transportation, and even space exploration. Thermodynamics is built on four fundamental laws, each describing a different aspect of energy and heat. These laws are the zeroth, first, second, and third laws. They provide a framework for understanding how energy is transferred and conserved. The laws apply to everything from tiny atoms to massive stars, making them universal in scope. By grasping these laws, we can predict how systems will behave, design efficient machines, and even tackle big questions about the universe. Let's take a closer look at each law, starting with the zeroth law. Zeroth law of thermodynamics might sound unusual, but it's essential for defining temperature. It states that if two systems are each in thermal equilibrium with a third system, then they are in thermal equilibrium with each other. This law allows us to use thermometers to measure temperature accurately. Without the zeroth law, the concept of temperature wouldn't be consistent or meaningful. It's the foundation for all temperature measurements and helps us compare the thermal states of different systems. First law of thermodynamics is all about energy conservation. It states that energy cannot be created or destroyed, only transformed from one form to another. For example, when you heat water on a stove, the chemical energy in the fuel turns into heat energy, which warms the water. This law is also known as the law of energy conservation. It's a powerful tool for engineers and scientists, helping them design engines, refrigerators, and countless other devices. The first law ensures that all energy changes are accounted for in any process. Second law of thermodynamics introduces the concept of entropy, a measure of disorder or randomness in a system. It states that in any energy transfer or transformation, the total entropy of a closed system will always increase over time. This law explains why heat flows from hot to cold, why ice melts, and why processes in nature are irreversible. The second law sets the direction for natural processes and is key to understanding why perpetual motion machines are impossible. Third law of thermodynamics deals with absolute zero, the lowest possible temperature where all molecular motion stops. It states that as a system approaches absolute zero, its entropy approaches a minimum value. This law helps scientists understand the behavior of materials at extremely low temperatures and is crucial for fields like cryogenics and quantum physics. Absolute zero is a theoretical limit, but it provides a reference point for temperature scales and thermodynamic calculations. Understand thermodynamics, it's important to know some key terms. These include system, surroundings, boundary, state, process, and equilibrium. A system is the part of the universe we're studying, while the surroundings are everything else. The boundary separates the system from its surroundings. The state describes the system's properties at a given moment, and a process is any change that happens to the system. Equilibrium means the system's properties are unchanging in time. Mastering these terms will make it easier to follow thermodynamic discussions. Thermodynamic systems can be classified as open, closed, or isolated. An open system can exchange both energy and matter with its surroundings, like a boiling pot without a lid. A closed system can exchange energy but not matter, such as a sealed container of gas. An isolated system exchanges neither energy nor matter, like a perfectly insulated thermos. Understanding these distinctions helps us analyze real-world processes and predict how systems will behave under different conditions. Thermodynamics properties are divided into state functions and path functions. State functions, like temperature and pressure, depend only on the current state of the system, not on how it got there. Path functions, such as work and heat, depend on the specific process taken. This distinction is crucial for solving thermodynamic problems and understanding energy changes. By identifying which properties are state or path functions, we can better analyze and predict system behavior. Work is a key concept in thermodynamics, representing the energy transferred when a force moves an object. In thermodynamic systems, work can be done by expanding gases, moving pistons, or even electrical currents. Calculating work helps us understand how engines and machines operate. The amount of work done depends on the process and the path taken, making it a path function. Work is central to many applications, from power plants to refrigerators. Heat is another fundamental concept in thermodynamics. It's the energy transferred between systems due to a temperature difference. Heat flows from hotter objects to colder ones, and this transfer drives many natural and technological processes. Understanding heat is essential for designing engines, heating systems, and even predicting weather. Like work, heat is a path function depending on how the energy transfer occurs. Mastering the concept of heat helps us control and utilize energy more efficiently. Internal energy is the total energy contained within a system, including kinetic and potential energy at the molecular level. Changes in internal energy result from heat added to or work done by the system. This concept is central to the first law of thermodynamics and helps us track energy changes during chemical reactions, phase changes, and other processes. By understanding internal energy, we can predict how systems respond to heating, cooling, and mechanical work. Enthalpy is a thermodynamic property that combines internal energy with the product of pressure and volume. It's especially useful for processes occurring at constant pressure, like many chemical reactions. Enthalpy changes tell us how much heat is absorbed or released, making it vital for understanding combustion, phase changes, and industrial processes. By measuring enthalpy, scientists and engineers can design safer, more efficient systems. Entropy is a measure of disorder or randomness in a system. The second law of thermodynamics tells us that entropy always increases in natural processes. This explains why things naturally move from order to disorder, like ice melting or gas spreading out. Entropy is a key concept for understanding the direction of processes and the limits of energy conversion. It also has implications in information theory and cosmology. Specific heat capacity is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Different materials have different specific heat capacities, which affects how they respond to heating and cooling. Water, for example, has a high specific heat, making it excellent for regulating temperature. Understanding specific heat is important for everything from cooking to climate science. Heat engines are devices that convert heat energy into mechanical work. Examples include car engines and steam turbines. The efficiency of a heat engine depends on how much of the input heat is converted to useful work. The second law of thermodynamics sets a limit on this efficiency, meaning no engine can be 100% efficient. Understanding heat engines helps us design better machines and reduce energy waste. Refrigerators and heat pumps are devices that move heat from one place to another. Refrigerators remove heat from inside and release it outside, keeping food cold. Heat pumps can work in reverse heating or cooling buildings. These devices rely on the principles of thermodynamics, especially the second law. By understanding how they work, we can improve energy efficiency and comfort in our homes and workplaces. Carnot Cycle is a theoretical model that describes the most efficient possible heat engine. It consists of 2 isothermal and 2 adiabatic processes. The Carnot engine sets the upper limit for efficiency, showing that real engines can never be more efficient than this ideal. Studying the Carnot cycle helps engineers understand the factors that limit engine performance and guides the design of more efficient machines. Thermodynamics, we often compare real processes to idealized models. Real processes involve friction, heat loss, and other inefficiencies, while ideal processes assume perfect conditions. By studying both, we can identify where energy is lost and how to improve system performance. This comparison is crucial for designing practical machines and understanding the limitations of theoretical models. Thermodynamic equilibrium occurs when a system's properties are unchanging in time, and there are no net flows of energy or matter. This state is important because it allows us to apply the laws of thermodynamics and make accurate predictions. Systems naturally move toward equilibrium, and understanding this process helps us analyze chemical reactions, phase changes, and more. Phase changes like melting, boiling, and condensation involve energy transfer without a change in temperature. The energy required for these changes is called latent heat. For example, when ice melts, it absorbs heat but stays at 0 degrees C until all the ice is gone. Understanding latent heat is important for meteorology, cooking, and industrial processes. Thermodynamics plays a vital role in chemistry, helping us understand how and why reactions occur. It allows chemists to predict whether a reaction will release or absorb heat and how much energy is involved. Concepts like enthalpy, entropy, and Gibbs free energy are essential for analyzing chemical processes and designing new materials. Gibbs free energy is a thermodynamic potential that predicts whether a process will occur spontaneously at constant temperature and pressure. If the change in Gibbs free energy is negative, the process is spontaneous. This concept is crucial for understanding chemical reactions, phase changes, and biological processes. It combines enthalpy and entropy to give a complete picture of energy changes. Thermodynamics isn't just for physics and chemistry, it's also essential in biology. Living organisms rely on energy transformations to survive, grow, and reproduce. Processes like metabolism, respiration, and photosynthesis all follow thermodynamic principles. By studying these processes, biologists can understand how life maintains order and overcomes entropy. Engineers use thermodynamics to design everything from engines to air conditioners. By applying the laws of thermodynamics, they can optimize energy use, improve efficiency, and reduce waste. Whether it's building power plants or designing spacecraft, thermodynamics is a cornerstone of modern engineering. Understanding these principles is essential for solving real-world problems. Thermodynamics isn't just for scientists and engineers, it affects our daily lives. From cooking food to keeping our homes comfortable, thermodynamic principles are at work. Understanding how heat moves and energy is used can help us make better choices, save energy, and live more sustainably. Everyday examples make these concepts relatable and practical. Thermodynamics has profound implications for our understanding of the universe. It helps explain the life cycle of stars, the expansion of the cosmos, and the ultimate fate of everything. Concepts like entropy and energy conservation are central to cosmology and astrophysics. By studying thermodynamics, we gain insight into the past, present, and future of the universe. Accurate temperature measurement is essential in thermodynamics. Thermometers use various principles, such as the expansion of liquids or electrical resistance, to measure temperature. These measurements are crucial for experiments, industrial processes, and even weather forecasting. Understanding how temperature is measured helps ensure reliable data and safe operations. Pressure is another key variable in thermodynamics. It's the force exerted per unit area and plays a vital role in processes like boiling, condensation, and engine operation. Measuring and controlling pressure is essential for safety and efficiency in many industries. By understanding pressure, we can design better systems and prevent accidents. Volume, the amount of space a system occupies, is a fundamental property in thermodynamics. Changes in volume affect pressure, temperature, and energy. For example, compressing a gas increases its pressure and temperature. Understanding volume changes is crucial for designing engines, storage tanks, and many other systems. Thermodynamic diagrams, like PV and TS diagrams, are powerful tools for visualizing processes. They help us understand how variables like pressure, volume, and temperature change during a process. Engineers and scientists use these diagrams to analyze cycles, optimize performance, and troubleshoot problems. Mastering these diagrams is essential for anyone working with thermodynamic systems. Heat can be transferred in three ways: conduction, convection, and radiation. Conduction occurs through direct contact, convection through fluid movement, and radiation through electromagnetic waves. Understanding these methods helps us design better insulation, heating systems, and even spacecraft. Each method has unique characteristics and applications. Insulation is all about reducing unwanted heat transfer. Good insulation keeps homes warm in winter and cool in summer, saving energy and money. Materials with low thermal conductivity are best for insulation. Understanding how insulation works helps us make buildings more comfortable and environmentally friendly. Power plants use thermodynamic cycles to generate electricity. Whether it's coal, nuclear, or solar, the basic principle is converting heat into work. Understanding these cycles helps engineers maximize efficiency and minimize environmental impact. Thermodynamics is at the heart of modern energy production. Cars, airplanes, and ships all rely on thermodynamic principles to move. Engines convert fuel into motion by harnessing heat and pressure. By improving thermodynamic efficiency, we can make transportation cleaner and more sustainable. Understanding these principles is key to designing the vehicles of the future. Spacecraft must manage extreme temperatures and energy needs. Thermodynamics helps engineers design systems that keep astronauts safe and equipment functioning. From life support to propulsion, understanding energy transfer is crucial for exploring the final frontier. The Earth's climate is governed by thermodynamic principles. Energy from the sun drives weather patterns, ocean currents, and the water cycle. Understanding these processes helps scientists predict climate change and develop solutions for a sustainable future. Materials scientists use thermodynamics to develop new materials with specific properties. By controlling temperature, pressure, and composition, they can create stronger, lighter, or more heat-resistant materials. This knowledge is vital for industries like aerospace, electronics, and construction. Medical devices, from incubators to MRI machines, rely on thermodynamic principles. Controlling temperature and energy transfer is essential for patient safety and effective treatment. Understanding thermodynamics helps medical professionals and engineers develop better healthcare solutions. Cooking is a practical application of thermodynamics. Heat changes the structure and flavor of food, and understanding these changes can help us cook better meals. From baking bread to grilling steak, thermodynamics explains why and how food transforms in the kitchen. Electronic devices generate heat during operation. Managing this heat is crucial for performance and longevity. Engineers use thermodynamics to design cooling systems, from fans to heat sinks, ensuring devices run smoothly and safely. Thermodynamics continues to evolve, driving innovations in energy, technology, and science. From renewable energy to quantum computing, new discoveries are expanding our understanding and opening up exciting possibilities. Staying informed about thermodynamics helps us shape a better, more sustainable future. We've covered the basics and advanced concepts of thermodynamics, from the fundamental laws to real-world applications. Understanding energy, heat, and work helps us make sense of the world and solve practical problems. Whether you're interested in science, engineering, or everyday life, thermodynamics offers valuable insights and tools. Keep exploring, and you'll find that thermodynamics is truly everywhere.